So welcome back, students. There was one aspect of Gauss's law that we did not cover, so I'll just cover that part too, which is a very important thing. And after that we'll do the problems. That is the field due to a uniformly charged thin spherical shell. It's very important. This is something that you may have come across even in your gravitational field lesson in the 11th standard. It's something similar. So you take a shell, like an egg shell, okay? You have a shell, and in this case, like you're going to have a spherical shell. I mean, you can ignore the thickness, but then there is a shell of charges. And now we are going to find out what the field value would be both inside and outside the spherical shell using Gauss's law. Okay, so this is what we will see now. So you have a shell. Okay, so now I can probably and this is a radius, say r. Now I'm going to find out what the field value of this shell of charges. There's a lot of charges on it. So it's a spherical shell. The field due to a spherical shell. Of charges. So the charges are now distributed over the surface of the shell. So I can talk about the surface charge density now. So it's no longer a point charge. So you have a shell like an eggshell, and charges are distributed all around, all over it. So I can now talk in terms of the surface charge density. So what's the total charge on the shell? Let's say the total charge on the shell is Q. Okay, let's say Q is the total charge on the shell. Okay. How can I express this? I can say that this charge Q is distributed over the entire surface area of the shell. So I'll say that I have a surface charge density sigma of Q by 4 pi r square would be the surface area of the shell, right? So that is sigma is equal to 4 pi r square, or I can write that Q is equal to 4 pi r square into sigma. So I can write it either way. So now I'm going to find out what the value of the field, electric field, due to this system of charges, shell of charges, both inside and outside the shell. Let me take this point. Let me take some random point here. I'll call this as A. Now I want to find the field due to all these charges inside at this point. So what is it going to be? Well, you see, if we take a charge here, and that charge, suppose it's all positively charged, the shell is positively charged, then that will have a field in this direction, right? Straight. And then if we take a charge here, and that will have a field in this direction. And if we take a charge here, and that will have a field in this direction, right? And all the charges will have their own fields at that point A. So now I need to find the sum of all of it. The sum of all these fields would be the field at point A. So how am I going to do it? Well, the way I'm going to do it is something like this. Okay. Let's say this point is at a distance r from the center. Okay. And notice that if we take any other point on this circle, inner circle, same distance r. Same distance r. So, by symmetry, I can argue that whatever E that's going to be here will be equal to the E here, right? Magnitude wise, of course. You can have a different direction here, but at least magnitude wise, you will have the same E here, and then the same E here, and then the same E here, and the same E here. By symmetry, I can argue that. It doesn't really matter whether I have a point here or here. Because, for this point, you have the closest point is this, and for this point, the closest point will be here. And then all the other points, like whatever you have here for this point, will be here for this point. And whatever you have here for this point, will be here for this point. So, by symmetry, I can argue that the E value that I'm going to have here for A will be the same for all the points on this small sphere inside, right? The imaginary sphere. Okay? There is no sphere inside, only the shell is present. Now I am trying to find E only for this point, but I am imagining this point to be on an imaginary sphere. And I know that all the points on the imaginary sphere will have the same E value because it's symmetrical about the center. So E will be the same for all of them. Okay, and now there would be. Now I can consider this to be my Gaussian surface. So this is my Gaussian surface, right? So this is my Gaussian surface. So what do we know? We know that E dot delta S, or the sum of the flux coming out, must be equal to the charge enclosed in that sphere. Okay, then what is the E dot delta S here? Okay, what is the sum of all E dot delta S? Well, you can see that assuming that it is in one direction here, in direction here, suppose it's in this direction maybe, or maybe here, whatever. Okay, I have the delta S part of the smaller imaginary sphere that will also be aligning with this E field if it is there. Then I can say that the sum is actually equal to E, which is common for all of them, and this area, right? The sum of all these areas. Okay, now I can remove the vectors because they are aligned. That E and delta S will be aligned similarly for all these small areas. So that would give me E to the sum of delta S, and that would be E into 4 pi this small r square. Okay, so that would be the flux coming out from the center. Okay, so the flux E, okay, the coming out from this sphere, not at this point alone, from the entire sphere will be equal to E into 4 pi r square. But I don't know the E value. But I know that if it is coming out, then if I take the E value, which is going to be common, it's going to be same for every point on the surface, and if you multiply it by the entire area, then that must be equal to the flux coming out of it. Okay. So what do we know? This must be equal to the charge enclosed by the surface by epsilon naught. But then what's the charge enclosed by the surface? Well, I have this sphere, but all the charge is on the outside. All the charge is on this surface actually. All the charge is on this surface. But there is no charge inside. But I take this imaginary sphere, but is there any charge inside? There is no charge inside the imaginary sphere. Because the charge is all on the surface of the sphere. But now I am considering an imaginary sphere inside this shell. So, do I have any charge inside that sphere? No, I don't. So, simply this Q enclosed will be equal to 0. So, 0 by epsilon naught, and that must be equal to 0. So, So I can equate these two now. If I equate these two, so this is 1 and this is 2. So E into 4 pi r squared is equal to 0. Okay? Okay, now look at this. 4 is not 0, pi is not 0, r is also not 0. Because I can imagine a sphere of a particular radius. So this term 4 pi r squared, this is not 0. Then what can be 0? Only E can be 0 to match this condition. So I can say that E is actually 0. So for a spherical shell, the field inside that shell is 0 for any point inside that shell. So if you have, if there is a lot of charge on the shell, and then if you sit inside, there will not be any force, electric force on you. Okay? So that is one part. That's one part of this definition, this derivation, basically. Okay. So the force inside E inside a spherical shell is always 0. Doesn't matter which point I take. So that is an amazing result. You may have lots of charges outside on the shell. You may have 2 coulomb, 10 coulomb, 1000 coulomb, 10,000 coulomb. Doesn't matter. But if you are inside the shell, there is no electric force on you. That's the thing. Okay? And that is for inside the shell. What about outside? Okay. So what about the outside? Well, I'm going to use the Gauss law for the outside too. Now, I'll consider this sphere. I'll draw a smaller circle. That's too big. So I consider this sphere. Now I've got all these positive charges there, or negative charges depending on what you want to have. This is the center, and this is my R, capital R. That's the radius of the shell. But now let me take a point, maybe here, okay, which is at a distance R from there. Now, all these charges will set up their own fields, right? So this will have this field, and this will have this field, this will have this field. So all these things will set up a field there. And then the resultant E will be the sum of all of it, all these forces. But you can easily sense that this E would be in this direction. Okay? Because if I take this point, then that will set E in this direction. Okay? And if you take a corresponding point on the other side, that will set E in this direction. So the horizontal components will cancel, then it will go up. So it's like a cone now. Like if you have a sphere like this, and if you want to find E at this point, this will set a field there, and this charge will set a field there, and this will set a field there, this will set a field there. Now you will see a cone of fields, and effectively you will only have one direction from the center going up. So, it's clear it is not 0. You can see that it is not 0 here. But again, if you take the point here, then it will be pointing in this direction. And if you take a point here, the same distance here, then it will be pointing in that direction. If a point here, it will be in the direction. But what do I know? I know that if I take a sphere centered at the center of the circle, this sphere, like this. Okay? So E at this point will be the same at this point if we have a same distance there, except the direction will be different. From here the direction is going to be different, but here the direction is going to be different, and here also the direction is going to be different. But you can see, you can easily see that you will have the same magnitude here or here or here or here. Okay? The same magnitude there. Okay? Now, again, if you want to find the flex which is coming out of the sphere, what do? It's going to be the flex coming out of this phi E, the total flex coming out of this sphere, the total flux coming out of this sphere, this imaginary sphere, can be written as the sum of all these E vectors dot delta S vectors. But you can clearly see something else. You see, the normal vector here at this point on the surface will also be in this direction, right? Will also be in the direction. And then the normal vector here will also be in this direction. So the normal vector here will also be in this direction. The normal vector here will also be in this direction as the field E. Okay. So this is going to be equal to sum of E delta S cos theta. But notice that cos theta is going to be 1 because the n vector, normal vector for the delta S and then the E vector are aligned. Okay, or either 0 or 180, depends. Like if you have negative charges there, then the angle will be 180, but if you have positive charge here, then it will be a 0. I hope you understand that part. So anyway, this cos theta part would be 1 in this case because we consider only positive things now, right? Okay, so it is simply sigma E delta S into 1. So E delta S, and then I can take E out because it's common value, because E is going to be the same at every point. Then sum of delta S, sum of all these small areas now. So the sum of all these small areas will give me the total area of the sphere. So that is going to be equal to E into 4 pi this r squared. So note here, and here r was smaller than r, but here r is greater than r. Okay, so that's the point I'm trying to say. Okay, anyway, in either case, this is what you did. So this is your stuff. So this is the total flux coming out of this sphere, right? I mean, it doesn't matter whether it's this sphere, smaller sphere, or this sphere, the total flux will be the same. Right? So this is equation 1 here, and then this phi e must be equal to what? This phi e must be equal to the total charge that is coming out. It will be equal to capital Q, sorry. Q by epsilon naught, and that is 2. And if I equate 1 and 2, since 1 is equal to 2, then I can say that E into 4 pi r squared is equal to Q by epsilon naught, or E, that gives me E is equal to Q by 4 pi epsilon naught r squared. So notice that even though I have a spherical shell of charges, it behaves for the points outside the shell, not for the points inside. For the points outside the shell behaves as if all the charges were concentrated at the center. You see, what is the difference between this and simply a charge at the center with Q and this distance r? Okay, this distance r. There is no difference, right? There is no difference at all between this. Like, if I have a charge at the center, for this point, what E value will I have? I am going to have E is equal to Q by 4 pi epsilon naught r squared. Likewise, even though the charge is distributed over a surface, it's not a point charge anymore, even though you have charge distribution in the form of a spherical shell, for a point which is lying outside that shell, the shell behaves as if it were a point charge placed at the center of the shell. Okay? But it's not, in reality that is not the case, right? Because if that were the case, then this should also work. No, that is not true. it behaves like this only for points which lie outside the shell. It doesn't behave like that for points which lie inside the shell. For the points which lie inside the shell, the E value is 0. Okay. So, this is one application of the Gauss's law. Or I can even take this idea of Q is this, and I can reduce this further actually. So what is E? E written as Q can be written as what? 4 pi r square is sigma, right? So sigma into 4 pi r square, so divided by 4 pi epsilon naught r square, r square. 4 pi, this is r square, this r square. This r square, capital R square, 4 pi r square, this one, right like that. So now 4 pi and 4 pi will cancel, then I can write E as simply sigma r squared by epsilon naught r squared. So either is fine, either that expression or this expression, they both mean the same thing. So the takeaway from this is that if I have a spherical shell of charges, then for the points inside the shell, there is no electric field. But for the points outside the shell behaves as if all the charges were concentrated at the center. It acts like a point charge for all points which lie outside the shell. But is the shell really a point charge? No, it is not. It behaves as if it were a point charge. But it is not a point charge because you have distributed the points, or distributed the charges over the surface of the shell. So I want you to understand that. So this part was not covered in the previous videos, so I am covering it now. So it must be clear to you, in my opinion. So with that, every concept in the lesson is covered. You see, this is something similar to what you did in your gravitation lesson in the 11th standard. So there also you did the same thing. You took a spherical shell of mass, okay, and then you're trying to figure out what the gravitational field was inside that shell. There also it was 0. But for the points which lie outside that shell, then the gravitational field existed, just like this. So there is a lot of similarity between the gravitational field that you studied in the 11th standard and then the electric field that you're studying in the 12th standard. Lots of similarities. They both are inverse square laws, and both fields are conservative, Gauss law can be applied for both of them. There will be mass, here will be charge, so that would be the basic difference. But otherwise, it's pretty much the same. Hope this is clear to you. Okay, let's go through the summary in the textbook, which is on page 42. 1. Electric and magnetic forces determine the properties of atoms, molecules and bulk matter. We know that. 2. From simple experiments on frictional electricity, one can infer that there are 2 types of charges in nature, and that like charges repel and unlike charges attract. By convention, the charge on a glass rod rubbed with silk is positive. That on a plastic rod rubbed with fur is then negative. 3. Conductors allow movement of electric charge through them. Insulators do not. In metals, the mobile charges are electrons. In electrolytes, both positive and negative ions are mobile. 4. Electric charge has 3 basic properties: quantization, additivity and conservation. We discussed that in the class. So quantization of electric charge means the total charge Q of a body is always an integral multiple of a basic quantum of charge, E. That is, Q is equal to NE, where N is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Proton and electron have charges plus E and minus E respectively. For macroscopic charges, for which N is a very large number, quantization of charge can be ignored. So I talked about it. We can treat them as continuous charges. Additivity of electric charges means that the total charge of a system is algebraic, sum of all individual charges in the system. We discussed that too. And conservation of electric charges means that the total charge of an isolated system remains unchanged with time. This means that when bodies are charged through friction, there is a transfer of electric charge from one body to another, but no creation or destruction of charges takes place. And then Coulomb's law, number 5. The mutual electrostatic force between 2 point charges Q1 and Q2 is proportional to the product Q1 Q2 and inversely proportional to the square of the distance R21 separating them. So mathematically, F21, force on Q2 due to Q1, can be written as Q into Q1 Q2 by R21 square with the direction vector R21, where R21 is a unit vector in the direction from Q1 to Q2. And K is equal to 1 by 4 pi epsilon naught is a constant of proportionality. In SI units, your unit of charge is coulomb. The experimental value of the constant epsilon naught is E naught is equal to 8.854 into 10 power minus 12 coulomb square per Newton per meter square. So the approximate value of K is equal to 9 into 10 power 9 Newton meter square per coulomb square. So all this we discussed in the class. Number 6. The ratio of electric force and gravitational force between a proton and an electron is, we did this problem, then it is equal to 2.4 10 power 39. Then number 7, superposition principle. The principle is based on the property that the forces with which two charges attract or repel each other are not affected by the presence of a third or more additional charges. For an assembly of charges Q1, Q2, Q3 and so on, the force on any charge, say Q1, is the vector sum of the force on Q1 due to Q2, the force on Q1 due to Q3 and so on. For each pair, the force is given by the Coulomb's law for two charges stated earlier. Then number 8. The electric field E at a point due to a charge configuration is a force on a small positive test charge Q placed at the point divided by the magnitude of the charge. Electric field due to a point charge Q has a magnitude of Q divided by 4 pi epsilon naught R square. It's radially outwards from Q if Q is positive and radially inverse if Q is negative. Like Coulomb force, electric field also satisfies superposition principle. We have seen that in the class. So number 9. An electric field line is a curve drawn in such a way that the tangent at each point on the curve gives the direction of electric field at that point. We discussed that in the class. The relative closeness of field lines indicates the relative strength of electric field at different points. If they are crowded, then the field is stronger in that area. If it is not so crowded, then it's weaker in that area. So they crowd near each other in regions of strong electric field and are far apart where the electric field is weak. In regions of constant electric field, the field lines are uniformly spaced parallel straight lines. So we saw that too. So if the field is uniform, then they'll equally spaced parallel lines. Number 10. Some of the important properties of field lines are: 1. Field lines are continuous curves without any breaks. 2. Two field lines cannot cross each other. 3. Electrostatic field lines start at positive charges and end at negative charges. They cannot form closed loops. So we saw all these things. 11. An electric dipole is a pair of equal and opposite charges q and minus q separated by some distance 2a. From a is measured from the center of the dipole. Its dipole moment vector p has magnitude 2qa and is in the direction of the dipole axis from minus q to plus q. So we have discussed that too. And 12. Field of an electric dipole in its equatorial plane, that is a plane perpendicular to its axis and passing through its center at a distance r from the center, is given by E is equal to minus P divided by 4 pi epsilon naught into 1 by a squared plus r squared to the power 3 by 2, and which is equal to minus P by 4 pi epsilon naught r cube if r is much greater than a. So the dipole electric field on the axis at a distance r from the center is given by E is equal to 2pr, so divided by 4 pi epsilon naught into r squared minus a squared the whole square, or which is approximately equal to 2p by 4 pi epsilon naught r cube for r which is much greater than a. So the 1 by r cube dependence of dipole electric fields should be noted in contrast to the 1 by r squared dependence of electric field due to a point charge. So we will discuss this also in the class. 13. In a uniform electric field E, a dipole experiences a torque tau given by tau is equal to P cross E. But this experiences a no net force if the field is uniform. Then 14. The flux delta phi of electric field E through a small area element delta S is given by delta phi is equal to E dot delta S. The vector area element delta S is equal to magnitude delta S with unit vector n, where delta S is the magnitude of the area element and unit vector n is normal to the area element, which can be considered planar for sufficiently small delta S. Okay? Then for an area element of a closed surface, n is taken to be the direction of outward normal by convention. So we will discuss this also in our lectures. 15. Gauss's law. The flux of electric field through any closed surface S is 1 by epsilon naught times the total charge enclosed by S. The law is especially useful in determining electric field E when the source distribution has simple symmetry. Okay, when the source distribution has simple symmetry, like, infinitely long wire which is uniformly charged, or an infinite plane which is uniformly charged, or take a spherical shell of charges, okay, whose surface density is uniform, something like that. Okay. So you have some symmetry, then it is much easier for you to use Gauss' law to find E value at a particular point. 1. Thin infinitely long straight wire of uniform linear charge density lambda, E is given by lambda by 2 pi epsilon naught r, the unit vector n, where r is a perpendicular distance of the point from the wire and n is a radial unit vector in the plane normal to the wire passing through the point. So you know which direction that is. And second, infinite thin plane sheet of uniform surface charge density sigma. E is equal to sigma by 2 into epsilon naught and unit vector n, where unit vector n is normal to the plane outward on either side. We've done that. Number 3, thin spherical shell of uniform surface charge density sigma. E is equal to q by 4 pi epsilon naught r squared r vector, unit vector in the direction of r, for small r greater than or equal to capital R, meaning the point must lie outside the spherical shell, and E is equal to 0 for all the points inside the shell. Okay, that's R is less than R. We did less than or equal to, but it's every point inside the R. Okay, that's better. You can keep it like that. Okay, so where R is the distance of the point from the center of the shell and capital R is the radius of the shell, Q is the total charge of the shell. So Q is equal to 4 pi r squared into sigma. So the electric field outside the shell is as though the total charge is concentrated at the center. The same result is true for a solid sphere of uniform volume charge density. The field is 0 at all points inside the shell. Okay? So the last point is this. Even if you take a charge distribution of uniform volume density, okay, there is like instead of a shell of charges, let's say you have an egg of charges. Okay. So there are charges inside as well as the charge on the shell. So then how do you do that? You can divide this volume, this solid shell, into a number of thin shells. Right? So you take a solid shell like this, okay, and then you divide it into number of thin shells. Okay, and if you take any point, then the shells above that point will not have any impact on that point in the field, but the shells below will have impact because like this point lies outside those shells, but inside the shells, outside this point. Okay, so you should be able to find this, and this is an exercise that you've done for gravitational field also. So it's pretty much the same thing that you'll be doing here too. Okay, so when we will do it when we come to it. So, but basically that's what it is. So even though we've done this for a spherical shell, even when you have a solid sphere, you can still use this idea by breaking the solid sphere into a lot of spherical shells, and using the results that we obtained, that for a point outside the shell, then you'll have the E value, but point inside, you won't have E value. So here you will have E values here, E values here, E values here, but this E value would be given by all the shells below this, and this E value would be given by all the shells below this. The shells above these points would not contribute to the point there. So it's like you can use that idea and do it, and we'll do it when we come across that. Okay, so this is the quick summary of that lesson. So I don't think it's very complicated, even though the lesson looks big, like 44 pages now. It is not actually that big. If you think about it, if you can organize the information given to you, the knowledge that you've gained, it's not a big lesson. It may look like a big lesson, but there are only a few core ideas, and from those ideas you should be able to reconstruct the entire lesson by taking logical steps from one place to another place, so from one idea to another idea. So you don't need to remember too much in this, even though like it looks like it's a big lesson and there are too many things in it. It's actually not. There are only a few key ideas that you need to remember, and once you have those key ideas, then you should be able to reconstruct the entire lesson without even referring to it. Okay? Hope this is clear to you, and then we'll get on with the problems.